Okay, we're going to start our discussion in designing the physical flow in a supply chain by introducing network models. So let's start with some common terms. There are many different types of networks that we're going to see, but they all consist of the same two things: nodes and arcs. Nodes are simply points. They're also sometimes called vertices, and so these could be distribution centers, customers, regions, plants, whatever. For our purposes, they'll be probably actual facilities, but they can be more abstract things in other network problems. Then you're going to have arcs or edges or links, and these are the things that connect the different nodes. And so you can see this could be a road network, this could represent flows, this could represent how cash is used on different projects. You can make it represent so many different things. That's the beauty of networks. Now a network then, or a graph, sometimes you see graph theory and network theory, it's just a collection of nodes and arcs. And there's a whole large domain here. If you're really interested, you can look into network models. We're going to focus on them specifically in the supply chain space. So there's some problems that you're going to see more often than others in supply chain that use networks. Let's talk about them briefly. And you've seen some of these before. First one, shortest path. So this is the problem if I want to go from node I to node J. Let's say that's New York and that the J is Los Angeles. So I have a road network. So the shortest path problem is finding what is the shortest, least cost, usually distance, through the network. What's my path from I to J? And so this is pretty much, we use this every day if we use any kind of mapping tool or software either on our phone or in our car. So this is a classic algorithm. It's kind of the root of almost every other algorithm that we're going to talk about. Then you've got the traveling salesman problem. And what the traveling salesman problem does, let me just clean this up just a little bit. There we go. So I've got these nodes still in these arcs. And what the traveling salesman problem says, let's start at one node. Let's call that the home. And what I want to do is find a path, or a tour rather, that visits each node once and only once, and then returns home. So let's say I'm going to go here, then I'm going to go there, then I'm going to go there. And I want to find the tour that is the shortest distance. And this is a problem that's been around for hundreds of years, seems trivial, but can be quite complicated. And so this is known as the traveling salesman problem. Then you have another problem called vehicle routing. Let me clean this little network up again, erase this. And so what this is, it's a little bit different, but it's very much related to the traveling salesman problem. Let's say I have a distribution center or a source node. So this is where a bunch of supply or physical product is, and then I have a bunch of locations I need to deliver to, whether these are stores, customers, whatever. So I've got this source node, the square, and I want to visit each of the demand nodes. And so I want to find the shortest tours, and this is each vehicle because I have multiple vehicles, and what tour will they take to visit all the different sites to deliver their product and return. So what you have is a bunch of vehicle tours, vehicle routing problem. So it's the least cost, usually least distance tours for vehicles to distribute all the product that's demanded from a single source node. Now the problem we're going to focus on the most in this lesson and the next several lessons is known as the min-cost flow problem. And so what that consists of is a little bit different. So we're trying to find the least cost flows of a certain product or a commodity through a network that satisfies demand at certain nodes. So I have certain demand nodes, called these customers, right? And I want to flow it. Maybe I have some distribution centers here, and I have some plants or sources. So I have product that goes from the plants to the DCs, and then each DC can go to each separate customers. This plant can also go here, and this DC could also distribute here. This plant could also go here. You see I have all these different flows. And so I want to figure out the lowest cost solution from my source nodes to my ultimate demand nodes in the least cost manner. So we'll talk a lot more about this problem. But as you see, as you get into this deeper, you'll see they all are very much related and they're all tied to networks. Okay, so let's talk about our approach in this module. Here are some things we're going to do. 3 things we will do when we talk about network modeling. First, our whole focus here is on the insights. I want you to understand what are the trade-offs involved with design, especially in this case, design of the physical flow. What are the trade-offs? How do I quantify them? What are the decisions that I'm making? I want you to understand the common approaches that are used in practice and each of their strengths and weaknesses. The second thing we're going to do is we're going to formulate math programs for optimization. We're going to solve these design problems using optimization tools, and we're going to formulate them into something called a math program. Now, there are other ways that we can solve or design a physical flow of a network. I could use seat of pants, for example, which means my experience. I know that I always want to have a distribution center here in Atlanta. I always know I want to have a certain structure, kind of based on experience. And you'd be surprised, or maybe not surprised, how often that happens. You can also use other techniques like heuristics. So if you know your demand is of a certain volume, I know I need that over X number of distribution centers. You have rules of thumb that can be applied. You could also use simulation. So I have my demand nodes out there, and I simulate what the demand is going to be, and I test out different network structures, number of distribution centers, how I flow, and the simulation will tell you which one is better or worse. It will never tell you what to do or to suggest a new solution. It'll only evaluate and rate the solutions or trials that you give them. But what we're going to focus on is the most common method. And like I said, it's using optimization. So I'm going to show you how to formulate a math program, not to solve an individual problem, but to solve a class of problems. And that's the critical thing, because what you're going to see is there are classes of different problems. And no matter how the data changes, you're solving the same problem. So this will also open the door for you to understand the literature a little better. So I'm going to be a stickler on the notation because it's important, because it provides clarity in making sure that you understand the problem. Third thing we're going to do is we're going to solve these things in spreadsheets, and specifically Excel and LibreOffice. Why do we use spreadsheets? They're the easiest tool to learn with. Everyone has access to them. They're all there. However, no one that I've ever run into uses spreadsheets to do network design. We use them for many other things in practice, but for supply chain network design, the problems are too complex, too sophisticated, so people always use some kind of specialized software package. I don't know any company that uses a spreadsheet. However, we're going to solve the exact same problems using spreadsheets. So it's just going to be a slightly smaller scale, because again, I'm here to make sure you understand the insights. So something we're not going to use, or we're not going to do. We're not going to dive deep into optimization theory. We don't have the time, and I didn't set the prerequisites for this class. It can be a very deep literature. It's a whole field. So there are other courses and references available for those that are interested in going deep. We're going to focus on applying optimization within spreadsheets to solve these math programs to mine for insights. That's what we're going to be doing in this course. Okay, so what's happened the rest of this lesson? We're only going to look at two problems. We're going to look at the transportation problem, which is kind of the simplest network flow problem out there. We're going to work an example. We're going to formulate the model. We're going to solve it in a spreadsheet. Then we're going to do the same thing for the next level of problem called the transshipment problem. We're going to work an example, formulate the model, solve it in a spreadsheet. Then we're going to talk a little bit about, okay, how do you do this modeling approach? So that's what we're going to do for the rest of the lesson.